This is Dubious Code, and we're looking at Project Euler Problem 5 solved in Python. So I just read this. I've done these all like years ago. And I just read this again for the first time right now. So it says 2520 is the smallest number that can be divided by 1 through 10 without any remainder. So it's what's the smallest positive number that can be divided by 1 through 20? So there's two ways we could do this. There's a kind of a brute force way and then a smarter way. The brute force way would just be keep going up from 2520 until we get this number that can be divided by all. Like just try from 1 to 20. The smarter way is because this is secretly a prime problem. We've already had problems 1 and 3 for primes, and I skipped ahead and did 7 and 10 in primes, so I have a prime function. But effectively, what this is saying is the prime factors of 1 is just 1. 2, the prime factors of 2 is 2. 3 is 3. 4 is 2 times 2. 5 is 5. 6 is 2 and 3. 7 is 7. 8 is 2 to the third power. 9 is 3 to the second power. And 10 is 5 times 2. So 2520 is going to be 2 times 3 times 2 to the second times 5. Now we already have a 2 and a 3 in our other numbers, so the 6 isn't doing any work making this 2520 bigger. So we're going to ignore the 2 at that 2 and a 3. 7. Now we need another 2 because 2 to the third power, we only have 2 to the second power, so 2. And we need 3 squared and 5 times 2. So we need 3 squared, 2 to the third, a 5, and a 7. So if we have a find prime factors. So if we were to find prime factors of 2520, prime factors, we expect this to be let's dot sort. We expect this to be 2, 2, 2, 3, 3, 5, and 7. And this is number 5. Answer is none. All right, so I'm doing something wrong. Find prime factors. Okay, so my sort is doing something wrong. 2, 2, 2, 3, 3, 5, 7. That's what I thought. It's already sorted, so I don't need to worry about that. So, effectively, what we did is we found all the prime factors of 1 through 10 and get a frequency count of them, and then only took the highest frequency. So we need to do the same thing for 20. So, Euler up, we'll give it to n. Here n will be 20. So for I in range 2 through n, here we won't pass it in range n equals 10. We'll start with 10 for range 2 to n. Then we'll make a dictionary of our prime factors. So factor count equals that. Say prime factors. Get from each of these numbers up to 10. So this will return 2 for 2, 3 for 3. For 6, it will return 2 and 3. And now, we need to get a frequency count for each of these. Freq count equals, we'll just do this as a dictionary too. For prime and prime factors, if prime and freq count, if we've already counted this, then we'll just add 1. Freq count sub prime equals freq count sub prime plus 1. Else, otherwise it's the first time, so it's equal to 1. This is the first time we've counted. So this is the frequency count for a given, this will be like the frequency count for 10. This would have a dictionary with 5 occurring once and 2 occurring once. And now, how do I get the keys and values out of a dictionary, out of a Python dictionary? I don't remember exactly, so let's look that up. Get Python keys and values from dicts. Items. For key value in dictionary.items. That's what we want. For prime frequency in freq count.items. So now we need to put it into this factor, the outer prime. So this will be if prime in factor count. If it's already in there, then factor count subprime equals max, the maximum of the frequency, and factor count subprime. So if there's already 1, if there's 1 in there or return, say, 2 2s, then this would have 2. If there's 2 in there, this would still be 2. And if it's not, else factor count subprime equals just our frequency. So this should get the unique maximum factors for everything from range 2 to 10. And so now let's just check it. For prime, freq, and freq count, product equals 1. For I in product times equals prime to the freq count power. And then we'll say print product is str product. All right, so we expect this to be, now there's a lot going on here. I wouldn't be shocked if I did something wrong, but I feel pretty good about this. But I wouldn't be shocked. I'm gonna, this something has gone wrong. I like this one though. All right, so we expect let's see. This should be I now, not 2520. We expect the answer returned here to be 2520 because 2520 is the smallest number from 1 to 10. All right, let's go for it. List index out of range. Primes index. This could be in my prime factors equals prime, find prime factors I. Okay, so something's wrong here. Find prime factors isn't working for like number 2, I assume. Int square root. We'll go, just go up 1. That's kind of janky. I don't know if that's going to work. Primes index. This is my previous prime code. It appears to be something a little janky with it. All right. Let's just make sure that works. I expect that this will break, and this is the reason it's breaking. So find prime factors up to 6. Let's see if this works. We expect it to return 2 and 3. Factors are okay, so that worked. But I think it's going to, let's see if it works at 3. This index out of range. What does it work at 4? I expect it to work at 4, so it's not working for 2 or 3. Yeah. So I pass 2 in. Int square root what if it has, it's probably because it's prime. Let's see, it's going to break on 7. Yeah, it doesn't do primes. Okay. Prime factors equals 0. Index equals 0. So we've gotten to the end of this. We're incrementing the index. While remaining is greater than 1. If I could just do a prime check. So if index greater than length prime factors, then prime factors dot append remaining. This should get my return to 7, and we'll just break. So now we should be able to get that the 7 is a prime factor of itself. Yeah, okay, excellent. Previously, we didn't need to figure out that it was a prime itself, and the code was wrong. So now we expect this to return 2520. Cannot unpack non-iterable int objects, line 42. Cannot unpack non-iterable int object. because this needs to be dot items, because it's a dictionary. Product is 9. Fantastic. Okay, so what am I doing wrong there? So let us print out, let's just print out the frequency count at this point. Print I freak count. See what we get. So for 2, we get 2, 1. 3, we get 3, 1. 4, we get 2 of 2. So that frequency count is correct. Wow. 9, we get 9, 1? That's not right. Why isn't this 3, 2? So why? Prime factors of 9 is wrong? Let's find prime factors of 9. Find prime factors of 9. Well, I'm having fun with this, but it's kind of a, sorry, it's not a great tutorial. All right, so it doesn't, find primes up to n. If index greater than blank prime factors and remaining I'll put this at the top of the loop and not the bottom. All right, so something going wrong here. So what primes are we returning for 9? We should expect these returning 2 and 3. Am I returning 3? 2 and 3. So why isn't... while remaining greater than 1. So we start with 9. Prime equals prime sub index. Start with 2. Print. Evaluating remaining plus prime. Let's see what we get here. Are we hitting this with 9 and 3? Evaluating 9 and 2. Greater than... primes is 2 and 3. Evaluating 9 and 2. Why isn't it? Print. Oh, not length prime factors? No. That's my issue. Length primes. There we go. 3 and 3. And And this should probably be int. All right, that is better. All right, I don't think this is still working now. So does it work for 4? Does it get the prime factors for 4? Does it work for 3? We're back out of range. Okay, we screwed something back up. Primes equals prime index. If index is greater than length of primes, greater than or equal to, because we're zero-base index. 3, excellent. That's working now. Still feel like I'm doing something wrong, because otherwise I wouldn't have returned product is 9. Let's get rid of these prints. So this was almost right before. 2, 2, 3, 1, 2, 2, 5, 1. 6 is a 2 and a 3. 7 is a 7. 3 2s. Okay, so that is right. And now let's see about the next one. The factor count outside the loop. And we get 3 2s, 2 3s, 1 5, 1 7. So that's right also. So everything is right up to there. And frequent, because I screwed up my variables, and it should be factor count. $25.20. Okay, so original plan was correct, more or less. I found an issue with my primes library wasn't great, and a couple other errors, but I believe it's working now. So now let's go up to 20 to in. And we don't need to print all these guys out anymore. And our product is 232,792,560. But you'll see the general strategy. You basically always should check your answer against this example. That's why they have it. 576. And that'll help you figure out if you're working correctly. Otherwise I could have gotten some random number and it wouldn't have worked. But that's problem 4. The solution was to find the prime factors, unique prime factors. And if you had good libraries, unlike me, you would have done it quickly. It took me about, 25 minutes? Thanks for watching.